If nu is 3, then you can create 4 equations just by using this thing. Completely general approaches here. But I used AB instead of A0, A1, A2. I used just ABC, ABCD to show you. But generally, this is the clue. So assume that you are asked to use 5th order polynomial to approximate the given set of points. Then you must create this thing with nu equal to 5. That means 0, 1, 2, 3, 4, 5. There are total 6 equations you can create. And then 0, 1, 2, 3, 4, 5, 6 coefficients. So once you create a system of 6 equations, you can solve the system and determine 6 coefficients, and then use 6 coefficients to approximate. Please browse the general idea and let me know. It is less severe, but it happens anyway. If you use like 12th order polynomial, then it is not great. So anything above 5 isn't very great. About up to 4 or 5 is about borderline. But anything higher than 6 or 7 or even 12 might be bad. So usually cubic is popular one, because it's very efficient, plus it is smooth enough. If it is too low, then it is not smooth enough, it is sharp. If it is too high, then it's difficult to handle. As you can see, the size of these things grow very fast, and unreliable plus complex cap. In any case, no matter what, somehow assume that someone suggests you to handle the case with 11th order, and they offer you money or degree. Would you do it? Would you do it? If you calculate 11th order, or let's make it more serious, 100th order polynomial, you will get a PhD right after you get it. Would you do it? I would do it, right? So if you find the 100th order polynomial, and by doing that you can get a PhD, I will definitely do it. So it is right.
Does that mean, though, the error is less at low points, you say?
Not necessarily. It is just condition given by the least squares definition. Least squares definition says under this condition, the error will be minimal no matter what. For instance, for the first order, error will be here. For the second order, error will be here. But it is not against each other. In other words, we don't compare error happening in second order and error happening in third order or error happening in the fourth order. Generally, higher order might have less error because it can bend more. If it bends more, it can have less error. If it doesn't bend at all, it may keep huge error. So your point of view is correct. If you use higher order, it might be better, generally. Yes? But we cannot even say that. The reason is this. If we look at the part, sometimes this could be the part of third order polynomial. It's almost, it looks like a line, right? So if we expand, even the third order can look flat, or third order can look like parabola. So we cannot just say this is bending, this is, because if we expand, even the third order function look very flat at some point. But as I mentioned before, take a look. Assume that we are approximating these things. Then first order polynomial cannot adjust, right? This might be the best we can do. But second order polynomial can even pass through the points. That means error is 0. So if we use higher order polynomial, then higher order polynomial may have less error, not directly compared by the theory, but general rule, right? General rule says higher order polynomial may have smaller error because it can bend. If it cannot bend, error is kept, like this example, right? The 3-point example. If we stick to first order approximation, no matter what, we cannot avoid error, right? But if we allow second-order polynomial, then second-order polynomial can exactly pass through the point. In other words, no error at all, as you can see, right? So, as you pointed out, if you use higher order polynomial, then it may have less error. But not because of the theory. Theory didn't say whether it is better or not. But general rule says if it's higher order, then you can reduce the error.
You have a set of data. How do you determine whether or not you want to approximate or interpolate the data?
For instance, if you are you are burning a CD, then you may want the exact thing instead of approximation thing. Then you may use interpolation. In other words, loss listing. You just keep all the details and then burn it. But if you are just sketching a few screen like background things, you don't have to be exact. Then you can approximate. So it's up to you to decide. So when I burned CD using MP3 file, it wasn't great. Some sound didn't. Some sound was not nice. So I found that some Microsoft product has lossless burning, and I used that, and then sound was great because it didn't lose anything. Exactly copied it on CD. Now, let's change the input dimension. Up to this point, we have X input, right? And then it generates Y height, right? X input generates Y height. But now, assume that we are handling points in two-dimensional plane generating heights, right? So each point generates heights. In other words, instead of X and Y, we use X, Y for input and Z for output. This is the reason in the previous case, I used Z equals something instead of Y equals something. Do you follow me? I said Z equals A plus BX instead of Y equals, because Y can play as an output or play as an input. So I want to keep Y, X and Y as input values, as input values. So now we can approximate the given function using this kind of polynomial. If it is flat, this is flat. And if we use higher order, we can bend. We can begin to bend. Do you follow me? So we can create a polynomial in two variables, X and Y. Or we can have three-dimensional input, and output could be different one, right? X, Y, Z input, and then something like W could be the output. Then how can you find this kind of thing? So generally, we can do it this way. Generally, we can do it this way. And this is the theoretical, right? This is the theoretical. So forget it. If you need this general thing, then you return back to general thing. But let's be specific. Assume that we want to find the plane like this. Find the plane like this. In other words, we want to determine A, B, C. Then how can you do it? We can do it by creating the similar system and then find the result. So let's practice. So -1, -2, and then 3, -2, 0, 5, and then 0, 1, 2, 1, 0, 3. Maybe 4 points could be enough, right? 4 points. There could be many more points. In programming, you can once you program, your program read X coordinate, Y coordinate, Z coordinate of the given points, and then store and then do all the things, right? Sum and all the things. We are doing hand calculations, so let's limit it to 4 points. And we want to find the plane approximating these things. So how can you determine A, B, C? Then use the formula. First of all, I will browse the formula and then remember the formula. Take a look. We count the number of points. So total 4 points, right? We count the number of points. And then we add x coordinates. And then we add y coordinates. And then we square x coordinates. We multiply xy, and then we square y coordinates. These are the things we need to do. And then the right-hand side is z, xz, and yz. So now you saw everything. So I will do these things to create the coefficients. So let's do it. We need to determine A, B, C. So A has the number of points, 4 points. Do you follow me? And then we add x coordinates, -1, -2, 0, 1. So -2. So I did that. And then we now add y coordinates. We add y coordinates. -2, 0, 1, 0, -1. And then we add z coordinates. 3, 5, 2, 3, 12. So if you don't understand, ask me. I just use the formula. The next thing, -2, A plus, we add x squares, -1 squared, -2 squared, 0 squared, 1 squared. So total is 6. And then we add xy. So -2 times -1 times -2, 0, 0, 0. So 2. And then finally, we are adding x and z product. -3, -10. So -13, 0, and then +3, -10. I'm just following the formula. And if you cannot get these numbers, let me know. So 3 square, sorry, you are right? So 3 and then 13, right? I somehow got the, thank you. 13 is correct. So please try to get these things. And then now we are adding y coordinates. Then it is -2, 0, 1, 0, -2. -2, 0, 1, so -1 times A. And then B is XY combination. XY combination 2, 0, 0, 0. 2B. And finally, y squared combination. 4, 0, 1, 0, 5. 5, and then the right side is y, z product. -6, 0, +2, -4. So I found all the numbers, and then I will now assemble A and then solve this. A equals 4, -2, -1, -2, 6, 2, -1, 2, 5. A is this one. B is 13, -10, -4. So it is this, right? 2.9. I will copy this. So the plane, the equation of the plane approximating the given point is found. Z equals 2.9 2.9 So this is the approximation we can get. So once data is given, we can find the plane best approximating the given set of points. Then what about the different order? I taught this thing, and then some student in class said, oh, I'm using these things all the time, and he needed second order function. Second order function, not just plane, but second order function. So x squared or y squared or combination. So he said, can you do it? So, of course. So I generated that equation from this general one. So if you need higher order one, ask me, then I will generate something like that. But this way more complicated because there are 6 unknowns. But it's doable, right? You can just do x, y squared combination, right? After solving 6 system, you can determine A, B, C, D, E, F, right? A, B, C, D, E, F, and then determine the two-dimensional surface. Right, the general one. So in fact, he was the beneficiary of this approximation thing because he uses this kind of data information and wanted to create the surface. So using this could. It's a two-dimensional input and one-dimensional output. So if we sketch it in 3D, then it is surface. Surface. So two-dimensional input generate height, right? So we have surface. So in this sense, in my opinion, I completely covered the least squares approximation generally and specifically, right? Generally like this in one dimension or two-dimensional input with one-dimensional output. So in 3D, we have. So sometimes I said 3D. 3D means total result, or even including result. Two-dimensional means not the input itself, but input and output combination. So in any case, I completely covered the approximation using least squares idea. And if you have a question, ask. So sometimes you do simulation, and you assume that you are creating the surface of your new car. Then you do the simulation and get nice points. For instance, less air resistant and something like that, or something. I don't know about engineering well, but in any case, assume that you have set of points. Then using these things, you can generate first order plane, second order surface, or third order, fourth, anything, right? And then you can create them. Then this portion is done. Then now theoretical portion. So theoretically, it is a little bit tougher than the previous one because in the previous case, just adding and subtracting, squaring will determine coefficients. Once coefficients are determined, you can solve this system to determine ABC. But now it is theoretical. So be prepared. I will use summary note and then explain line by line. Explain each thing line by line. So take a look. Generally, we want to approximate not just set of points. Set of points has a finite number of points, right? A finite number of points. Instead of handling finite number of points, we want to handle infinitely many points, or generally a function. So it's way different than just a few points, right? Do you follow me? So instead of handling a few points, we are now handling infinitely many points, or generally a function. How can you approximate a function? In other words, assume that e to the x function is given. How can you approximate that kind of function, e to the x function? So we have general theory. Assume that someone gives you the tolerance boundary, like, oh, the tolerance should be 0.001. So your error should not exceed 0.01. So someone gives you the tolerance, like epsilon. Then there is a theory supporting it. There exists, right? There exists a polynomial having difference less than the one that you gave, epsilon, right? 0.01 is always 001, no matter what. Theoretically, it exists. So theoretically, you can find a polynomial approximating any continuous function. Any continuous function can be approximated by a polynomial in epsilon range, in your tolerance range. Any function can be represented by a polynomial, but problem is here. That polynomial may have very high degree, like degree 1 millionth, or x to the power of 1 million, or x to the power of 1 trillion. So in this sense, theory doesn't help. There is a theory. Theory itself is not applicable. Do you follow me? Because theoretically, there is a polynomial. But what order polynomial? It could have power x to the power of 1 trillion. There is no point, right? X to the power of 1 trillion might not be possible to implement in general computer. So it might be. So we are not very interested in this direction. Then the next direction you can follow is using norm. And norm is checking whether two functions are close or not. So there is one function and there are two functions. Then we want to check whether two functions are close or not. In what sense? In what sense will be explained. If you pick the biggest difference, right? If you pick the biggest difference, then it could happen here, right? It could be the biggest difference. Then f minus g has the biggest difference, and then that biggest difference, like 2, right? Could be the norm of this thing. Then in this sense, the norm is 2 in this sense. Do you follow me? But generally, they could be very close. In other words, generally, they could be very close. And somehow, at the end, bad thing happened, and the norm happened to be 2, right? Generally, they are very close. And then it happened to have 2 at the end. 2 functions, right? So how can you distinguish this kind of thing from the above thing, right? Generally, they are very close, and at the end, it has some difference. So to capture these kind of things, mathematicians developed the norm, such as 2 norm, or generally, P norm. So mathematicians developed a norm to distinguish one from the other. Why? Because one norm can capture something, but something may be lost, right? Something, for instance, take a look. The distance 2 means they are 2 units away generally, but as you can see, they are very close, right? They are very close, only 2 units away at the end, right? Take a look. Does this say everything or not everything? It says something, but it may not be everything. Because of this reason, people defined 2 norm and P norm and different norms. So if you clearly understand the reason why we are defining norms, then I will continue. But if you don't understand the reason, let me know. So norm will be defined to capture the differences happening in different ways. Sometimes the biggest distance may happen, right? At some point. Sometimes they are very close, but at some point they have biggest distance. Then how can you capture the difference between 2 cases? So I will define the norm. So instead of just f minus g, we call the whole thing, let's call this whole thing f generally. Then I will define the norm. So norm will be defined this way. Oh, norm of p norm is nothing but integrating the function absolute value to the power of p function from the endpoint, one endpoint to the next endpoint, right? One endpoint to the next point, and then taking pth root. Why? Because we took pth order, right? Pth power. We now take 1 over pth power, right? Because we use pth power, we take 1 over pth power. This is the general definition of p norm. So I will calculate p norm with you. So let's do it. It's a little bit theoretical, but this will be used in the future. So assume that f function is cosine x. Assume that x is cosine x, and then p happen to be 2. P happen to be 2, and endpoints are from negative pi to pi. So this is the situation. Yes? Anything, sometimes different, but generally any function can have norm. That instead of worrying about two functions, just any function.
We're trying to find out
Two functions are close, right? Right. So it could be the difference of two functions, but I want to generalize it. In other words, instead of just worrying about the distance of two functions, just generally, I want to define the norm of any function. Then, let's do it. According to this, what you need to do is doing the integral from minus pi to pi, and then cosine x squared, because p is 2, dx, and then 1/2 power later, right? This thing, whole thing, to the power of 1/2. So this is the norm of cosine x, right? Cosine x norm 2. Do you follow me? So we can determine the norm of any function. Instead of just differences, we generalize the concept. If you don't understand, ask me. We completely generalize the concept. Then let's do the integral. If you do the integral, cosine squared is 1 plus cosine 2x over 2, and then minus pi over pi. Then this equals 1/2 x minus pi to pi. And if we integrate this thing, then it is 1/4 sine 2x from minus pi to pi. If you use pi, then sine 2pi is 0, negative pi is 0, so this is 0. And it is 1/2 pi minus negative pi. So it is 2 pi over pi, so it is pi. So the norm of cosine x, true norm of cosine x is square root of pi. So I could determine the length of the function. Length is not very intuitive word. The norm might be better, right? Norm of cosine x is square root of pi. If you don't understand, ask. Then this is the task. Find the norm of sine. Under the same condition, find the norm of sine function. What is the norm of the sine function? So please find the norm of the sine function. Right, same interval, everything is the same. Norm of the sine function is what? Wow, how did you? Yeah, right. It is square root, but practice. So you have 1 minus cosine 2x here. 1 minus instead of 1 plus. And as you know, cosine portion didn't even contribute at all in the integration. The cosine portion. So we can get the same result, right? So sine x norm is also square root of pi. Any questions? So with hand calculation is tough, but if you have Maple or MATLAB, then you can ask the computer to do the integration and then do the pth root, right? The computer will do this calculation. Now the next thing is this. What about one norm? The same interval. What about the one norm of cosine x? One norm of cosine x equals, by definition, integrating it from minus pi to pi, this function, absolute value, dx. Do you follow me? Then we should know where it is plus. So it is plus between, I will show you. It is from minus pi to pi. And if you sketch the cosine graph, it looks like this. So from minus pi over 2 to plus pi over 2, it is plus. So from minus pi over 2 to pi over 2, it is cosine x dx. And then from minus pi to minus pi over 2, absolute value of cosine is negative cosine x. And then similarly, from pi over 2 to pi, minus cosine x is plus. Right. Absolute value means cosine x should be always positive or non-negative. More precisely, cosine x should be non-negative. How? In this interval, cosine is non-negative. In this interval, negative cosine is non-negative. In this interval. So it's nothing but just integration. Then let's finish it. If you integrate, then it is sine x, right? If you integrate cosine is sine. And if you integrate this thing, then it is negative sine x. And if you integrate the negative sine x, so if we plug this in, sine pi over 2 is 1, and then negative pi over 2 negative 1. Done. And sine pi over 2 is negative 1, right? And then 0. And then minus sine pi is 0. Sine pi over 2 is 1. Done, right? Because of this, what happens? We have 2 plus 1 plus 1, 4, and one norm of cosine x is 4. So conclusion is one norm of cosine x is 4. But as the interval changes, the norm changes, right? If we reduce the interval from negative pi to pi to negative pi over 2 to pi over 2, this portion disappears. This portion disappears, right? Then just 2 survives, right? So depending on the interval, the norm changes. Do you follow me? The norm changes. Please browse this and ask questions. Please find the one norm of sine function. one norm of sine function. So one norm of sine function is also 4. If you didn't get it, let me know. So we calculate one norm, two norm of sine and cosine. Now I will calculate the infinity norm unless you have questions. Yes. Yeah. That one is the least squares. We are just defining norms, and then later we will use some norms to define certain approximations. For instance, two norm means least squares approximation. Infinity norm means minimax approximation, and so on. Now, infinity norm. So, what do you think will be the infinity norm of cosine x? The definition is this. Infinity norm uses integral, but integral with infinite power is impossible to calculate. So people did limiting process. And limiting process tells this maximum of the given function in the interval, right? Maximum of this given function in the interval. Assume the interval doesn't cover everything, then we should check what is the maximum value inside the interval. What is the maximum value of cosine from negative pi to pi? 1, right? 1. So infinity norm is 1. Please calculate the infinity norm of sine function. So infinity norm is 1. So you should know why definition suddenly changed, right? Why did definition suddenly change? Because p goes to infinity. So we did the limiting process. When you do the limiting process, you will get the maximum. So now you could handle any norm. If you have some kind of calculator or some kind of computer algebra system, you can do 3 norm, 4 norm, 1/2 norm, any norm, right? You can do any norm. Excuse me. Then as far as norm is concerned, you master the norm. Now it's time to generalize even further inner product. Generalize even further. So we use this kind of notation. Instead of saying f multiplied by g, we use parentheses. So it's called inner product of f and g. We are multiplying f and g, but not straightforward multiplication, but some kind of rules should be followed. Instead of direct f multiplied by g at individual point, we apply the rule. And generally, it is written this way. Oh, it is integral from outer, right, from one boundary to the next, and then weight function, and then f, and then g dx. So this is called the inner product. Weight given by the problem. Weight could be 1. Weight could be a certain function. So weight multiplied by f by g, integrate is called inner product of f and g. Why do we care about it? Because we will use this thing with different weight in the future. Weight is given by the problem or by the general set. We don't. It's just weight is given. So take a look. Find the inner product of sine and cosine, right? Sine and cosine function with minus pi to pi, and weight is 1. So what is the inner product of sine and cosine? Please find. Then I will show you, and then later I will assign something. Inner product of sine and cosine equals from minus pi to pi, weight is 1, and then f is sine, g is cosine, dx. Right? This is the definition of the inner product of two functions. Then sine and cosine multiplied, this is 1/2 sine 2x. So sine 2x is integrated. Then negative sine 2x. So negative sine 2x with 1/2. That gives us 1/4 by the chain rule. Cosine. Sorry. We don't even have to do any. It is an odd function, integrate from negative pi to pi, so 0. 0. Odd function, sine 2x is an odd function. When you integrate odd function from negative a to negative a to plus a, then it is 0. So the inner product of sine and cosine is 0. Later, we will use this thing to determine perpendicular functions, or more generally, orthogonal functions. How can you define two functions are orthogonal or perpendicular? We can determine two vectors are perpendicular or not. But how can you say two functions are orthogonal? So we will use this thing to define the orthogonality. How? When two functions have inner product equal to 0, then we call two functions are orthogonal. These kind of concepts will be required when we generate approximation. So in this sense, this section is tough because it requires certain level of mathematics, abstract mathematics. But in any case, I'm very slow in covering all the details. So please find the inner product of sine x and sine x. Please find it. What is the inner product of sine x and sine x? We did this calculation before. You can recycle the result. Anybody who finds it, tell me. Pi, right? What about the inner product of cosine and cosine? Same pi, right? So we can do inner product of these. In fact, we could have defined the p norm by using inner product. Well, how? Inner product square root of something, right? That is the one that you can define. So I covered some abstract stuffs and a few more, and then we will begin to use these things to define possible approximations. Then it's time to apply these things. Why did we care about these kind of norms or inner products? You will see very soon. First of all, we studied about the infinity norm. And for instance, two functions are measured, the distance two functions are measured by the difference infinity norm. Then this kind of approximation, assume that function is given, and now we are using, instead of g, I will use polynomial. Instead of using g, I will use a polynomial. In other words, this is the function given by the problem, and this is the polynomial that we find, right? Polynomial that we find. Then it's an approximation, right? It's an approximation. If we minimize this kind of distance, then we call this polynomial minimax approximation. Minimizing the maximal distance, right? Minimizing the maximal difference, minimax polynomial. Do you follow me? Minimize the maximal distance, maximal difference. Yes? We are minimizing this quantity. Right. Right. In other words, if you use infinity norm and make this infinity norm smallest possible, right, then it's called minimax. If you are using the same thing, everything is the same, right? Infinity becomes 2, then we are calling the polynomial the least squares approximation. Right? Least squares approximation. So these are two popular cases, minimax and the least squares approximation. And what else? We use weight, right? Weight and inner product, right? Weight and inner product. Then these will generate some popular approximations such as the Zandro approximation, Chebyshev approximation, and Laguerre approximation that we will cover. So we will use abstract theories to derive these approximations. So please browse the idea and ask questions if you don't. Then I will begin to cover the easiest thing. Any questions? Yes.
Can we back up to the f minus p there? I'm trying to imagine you have one f of the p is a set of data that gives you've got say some polynomial that you're trying to see how close the data is to.
Mm-hmm. But in this case, we are handling not just a set of data or a number of a few points. We are handling infinitely many points or a function. So a whole new different idea is required because we are not just handling a few points. We are handling a function. We are approximating a function. Then I will mention about some kind of background. Generally, minimax is closer to our theorem, Weierstrass theorem. I will show you. Weierstrass theorem says when you have a polynomial, right? When you have a polynomial, we can find when you have a function, we can find the approximating polynomial, making it very close to a function, right? So minimax polynomial is very close to this theorem, right? Because of this reason, people regard minimax as the best because it is very close to the theorem. But the problem is the calculation, and I will show you the reason. Take a look. I want to approximate E3x function from 0 to 1. So I want to approximate this E3x function from 0 to 1 using a line. Using a line. In other words, I want to find a line having the minimal difference. Having the minimal difference at any point, right? Find it. Then we can make difference here, maximal possible difference here, epsilon, right? We can have maximal distance here, and we can have maximal distance here, epsilon, and we can have maximal distance here. This might be the best setting. Do you find other way of locating maximal distance than this thing? Where can you locate maximal distance? If you locate the maximal distance at one point, for instance, right here, then this distance may be bigger than this distance. Do you follow me or not? Do you clearly see the reason why I did the above thing instead of this thing? In other words, if we approximate the given function using a line and use this idea, then the distance that we can get from this thing will be bigger than the distance that we will get from this thing. Because of this reason, I use this strategy. But if you don't understand this strategy, ask me. I want to minimize the difference. If you use this idea, the possible error is huge. So to reduce this thing, I lower this down and then distribute this difference to this portion, the other end portion, and then middle. Then I can somehow halve this one, right? Do you follow me? So I have this one. I lowering down instead of keeping it in this form. So this way, so this line is called the minimax approximation with order 1, right? With order 1, with degree 1. Polynomial, right? Polynomial with degree 1. It means a line. If you still don't understand, ask me. So I will show you how to find this thing after the break. So I will wait, and then you may browse these things, and we may resume at 3.